Hello, this is my projectile motion experiment. And the purpose of this lab is to observe an object being thrown and moved in the shape of a projectile and compare with the computational model with and without a drag force applied. And the overall result will be the computational model with the drag force applied will be more closely aligned with the real-world observations on a graph. The fundamental principle of this lab is the Newton's second law, which states that the interaction between the system and its surrounding results in the net force related to the change in the momentum, which is the observed motion of the system. And the main equation used in this lab is position update formula. This one is derived from the velocity equation, as well as the velocity update formula, which derived from the momentum principle, which is the Newton's second law. And we also have F-net calculation in this lab. It involved the gravity, the one that on the Earth's surface, and the drag force was in the negative direction of the velocity. For the observation model setup, we have the system is the rapid paper ball weighs 3 grams, and the surroundings are the air resistance and gravity. And using Projectile to analyze its motion. From the analysis, we found its initial position and divided by the time we get the initial velocity. And the last time lapse is as 1 second. And we're gonna put this into the closed graph on the next slide. The first computational model is the one with the drag force, and for the initial condition we have the mass of the ball and the initial position and velocity of it from the tracker, and we also have g equal to 9.8, and the big constant for drag force is equal to 0. And for the while loop calculation we have it ends at 1, which is the last time frame from the tracker, and for the net force calculation we have drag force and gravity applied it. And we also have velocity and position update formula, and as a result this is what we get. And there are only velocity arrow and the gravity arrow, there's no drag force arrow yet, and this is a graph for it. And with the drag force applied, we only change the big constant into 0.001, and this is our result. And here we have the drag force arrow, and it is opposite to the velocity arrow. Here is the three models put in together, and the orange is the computational model without drag force applied, and so it goes much further away comparing to blue and green. And green is the computational model with the drag force applied, and as you can see that it is much closer to the observed motion in blue. Here is some sources of error in my experiment. Firstly is the shape of the curve. It is a little sharp parabola shape. As a result that my observation model in blue has the highest y value, even higher than the orange graph, so there is no way for the green graph to match my blue graph. Secondly is the paper wrapper is not perfectly round. It has some hole and empty space in it. As a result, the air resistance have more surface area to act on it, and also affect the shape of my parabola curve. And lastly is the computational limit. I can't go for a lower b value for a better match because the green graph is almost matched the orange graph, which is the one that without drag force. Some additional questions. Is there my model has the terminal velocity? And the answer is no. As we can see here, this graph is the one that without drag force, and this is the one with drag force. And both of them has a change in velocity. So none of them is in terminal velocity. So to create an experiment with terminal velocity, instead of throwing the ball, I should drop the ball from a high enough distance to have the drag force to balance out the gravity, and eventually achieving a zero net force, which is a requirement for terminal velocity. What if I throw the ball straight up? As a result, it's gonna take the ball longer to reach the ground with the same speed as in my experiment, because according to the Newton's second law, in the velocity update form, the vertical velocity will affect the change in time. As we can see here, the y component of F-net is minus mg, so the m gonna cancel out, leaving with the negative g times delta t. Meanwhile, in the horizontal velocity, the x component in F-net is equal to 0, so it's gonna cancel out this whole term, leaving the velocity stay constant and doesn't affect the change in time. So despite that, a decrease in the horizontal velocity and increase the amount into the vertical velocity will increase the time for the object to reach the ground. And that is my experiment. Thank you for listening.